Assalamualaikum, my name is Hananji binti Alfi, and this will be the presentation for experiment 5 bending moment from group 5. So the group has 4 participants, which is me and Muhammad Amir Ashraf bin Muhammad Azali, Nurul Azwa binti Kamal, and Shafiq Hidayat bin Johan. I will be also presenting the introduction for this experiment. So firstly, bending moment occurs when a force is applied to a structure, such as a beam, causing it to bend down under a load. So from the picture that I have provided, you can see how the force is equally placed on the beam and how the bending moment curves down from the beam. Other than that, it can manifest at various points along the beam, and it will result in compression at the top and tension at the bottom of the beam. And as you can see, the force that is applied further away from the pin is the bending moment is much larger than the one that is closer to the pin. Also, the location of these loads has a significant impact on the distribution and magnitude of bending moments within the beam. So from the picture, you can see the force is positioned in the middle of the beam, and so the distance between the two pins is equal. And you can see how much bending moment is higher in the middle because the force is only placed at one position. So there are two objectives in this experiment. The first one is to measure the bending moment under varying loads applied at a fixed distance. Secondly, to investigate how changing the distance while maintaining equal loads affects the bending moment. I will explain furthermore in scope. So in this part, I will be explaining even further on how the experiment were held. So for the first part, 3 load hangers P1, P2, and P3 will be placed with an equal weight of 2 Newton. And P2 position is fixed at 300 millimeters from pin A, but P1 and P3 are placed in different distances with ratio of 1 to 2. P1 will be 50, 100, 150, 200, and 250 millimeters from P2, and P3 is 100, 200, 300, and 400, 500 millimeters from P2. So P2 will be the constant load hanger in this part. So for part 2, the same 3 load hangers will be used, which is P1, P2, and P3 are placed in fixed position of 150, 300, and 650 millimeters from pin A. The distance between pin A and pin B is 800 millimeters, and the weight used are 5, 10, 15, and 20 and 25 Newton. So when the experiment were held, the load will be placed one at a time.
Assalamualaikum and hi. I will explain about the theory on this experiment. A bending moment is the reaction induced in a structural element when an external force, such as P, are acted to the structure as in the figure below. So the element can also be bent if a moment is applied. The stresses can be determined by finding the internal forces and internal couples that act on in cross-section of the beam. When a beam is cut through, the bending moment at A are assumed to be positive in the direction of counterclockwise or as shown in the figure below. However, it is vice versa for the beam at B is considered. To calculate the equilibrium of moments for part A of the beam, Ms equals to Ra reaction A multiplied by the distance of A. Next, equilibrium of moments for part B of the beam, Ms equals to Rp reaction B multiplied by B minus P times by B minus L.
Hello, Assalamualaikum. So I'll be presenting the experimental setup for this experiment. From the left, we have the beam support A, which is point A, and on the right, we have beam support B, which is the point B. Both of these beam support is used to set our total length on the beam, and we chose the longest possible total length. Next, we have P1, P2, and P3. which is the load hanger where we put our load at, and also it is the manipulated variables in this experiment. P2 is fixed, so the place won't be changed for the whole experiment. Next we have hinge. That is where the bend happened. That's where the bend occurs, and the bending on that hinge will affect the spring scale value and also the bending moment value. And then next we have the spirit level. It is an item that we use to make sure that the beam is in balance, and before we measure the spring scale, we will make sure that the bubble inside the spirit level is on the right area so that the beam is balanced. And then next we have spring scale, which is where the force will be calculated at, and where we measure the force from the bending that happened on the hinge. So yeah, this is the experimental setup that we use in this experiment.
The methodology of the experiment. First, the procedure of the experiment is divide the beam into two halves. Then, join the smaller A and the larger B by a joint to create a frictionless hinge. A 150mm level arm underslung spring balance produces a moment of resistance around the hinge. To create a load, install 3 load hangers in the beam. The beam is supported by 2 bearings on stands. After each load change, perform spring balance and record the reading of the spring balance. 150 times the change in the spring balance reading equals the measured bending moment in millimeters. Part 1. The effects of the position, distance of P1 and P3 with loads towards the bending moment of the beam, which is P2. So the first thing to do is place 3 load hangers as desired. Align the beam until the position of the air bubbles is located at the center of the spirit level, which is as shown in figure 3.1, and was secured to the beam with cellophane tape, and P2 was made sure to lie on the beam stand as shown in figure 3.2. Secondly, record the initial reading of the spring balance in table 1. Thirdly, put the weights on all of the 3 hangers, realign the beam until the air bubbles of the device is located at the center of the spirit level, as shown in figure 3.3, and record the new balance reading using table 1. And repeat the experiment with different positions as shown in table 1. So here's the part 2 of the experiment, which is the effects of different loads at the P1, P2, and P3 on the bending moment of the beam. So for the procedure, firstly, set up the beam so that the bearing pin in part B is 300mm from the left hand support and 600mm to the right hand support. Secondly, load hangers P1 and P3 were secured to the beam using cellophane tape, and P2 was made sure to line on the beam stand as shown in figure 3.5. Thirdly, place one load hanger on the middle of the smaller part of A of the beam, and one on the larger part B, and the third one at the joint just over the bearing pin. Align the two parts of the beam using the spirit level adjustment and record the initial reading using table 2 as shown in figure 3.5. And then hang the 5 Newton weight on P1, realign the beam using bubble level adjustment, and record the new reading on the spring balance using table 2 as shown in figure 3.6. Next, the difference between two readings is the effect of applying the 5 Newton weight on the beam. Record the distance by using table 2 from this weight to the right hand support. Lastly, repeat the experiment by using the hanger over the bearing pin and then the hanger on part A. Lastly, repeat the whole procedure by using 10 Newton, 15 Newton, 20 Newton, and 25 Newton load as shown in figure 3.7, and also record in table 2.
So this is the result that we obtained from the experiment of variable distance. And this is the result that we obtained from the experiment variable loads.
So here is the calculation used to part 1. So as referred to the diagram showed, when distance P1 to P2 is 50 mm and P3 to P2 is 100 mm, we already mentioned that the load on P1, P2 and P3 are constant, which is 2 Newton. So RA plus RB is equals to P1 plus P2 plus P3, which we can get 6 Newton. So in order to find the value of RA and RB, we are taking clockwise moment as positive direction, which means P1 times 250 plus P2 times 300 plus P3 times 400 minus RB times 900, which we can get the value of RB, which is 1.22. And when we are substituting the value of RB into the previous equation, we can get the value of RA, which is 4.78. So in order to find the theoretical bending moment, we have to take anti-clockwise moment as positive direction. So the calculation made is moment equals to negative RA times 300 plus P1 times 50 minus P3 times 100 plus RB times 150, which is we can get the value 1351 Newton millimeter as the theoretical bending moment value. So in order to find the experimental bending moment value, we need to times the value of the net force obtained throughout the experiment times 50 plus 100. So we can get 1500 Newton millimeter as the experimental bending moment value. So this formula is used to all distances throughout the whole experiment in the table to find the theoretical and experimental value.
Assalamualaikum warahmatullahi wabarakatuh. My name is Hannah Indonesia and I will be presenting for the calculation for part 2. So in this part, I will only be explaining the load 5 Newton and you can refer the same calculation for the other weights. So for this part, when P1 is equal to 5 Newton, P2 and P3 will be 0 Newton because only one force is applied. And we can find the total of force in pin A and pin B, which is 5 Newton, and find the moment at A, which is 0, from P1 and pin B. So P1 is 150 millimeters from pin A and pin B is 800 millimeters from pin A. We can substitute the value and we get the force in pin B, which is 0.938 Newton, and then substitute it in equation 1 to get force in pin A, which is 4.062 Newton. And after getting the value force in pin A, we can find the moment at constant, which is at P2, from pin A and P1. So pin A is 300 millimeters from P2 and P1 is 150 millimeters from P2. And after substituting the value, we can get 468.6 Newton theoretically, and from the experiment we get 5.8 net force, and we got the 870 Newton for the force. So in this part, for P2 will be 5 Newton and P1 and P3 will be the one with 0 Newton. The same, the total for force in pin A and pin B will be 5 Newton. And moment in A will be 0 from P2 and pin B. So P2 is 300 millimeter from pin A and pin B, the same will be 800 millimeters, and if you substitute the value, you can get the force in pin B, which is 1.875 Newton. Substitute in equation 2 to get the force in pin A, which is 3.125 Newton, and we can get the moment at constant, which is in P2, from only pin A because the weight are placed in the constant. So pin A is 300 millimeters from the constant, so we can get the force of 937.5 Newton. And now we can find the moment at constant, which is this one is from the experimental, so 7.8 is the net force, and we 1170 Newton. So last but not least, for P3, it will be 5 Newton, and so P1 and P2 will be the one with 0 Newton. So the total force in pin A and pin B will be 5 Newton. We're going to do the same method of finding moment in A, which is 0, from P3 and pin B. So P3 is 650 from pin A, 650 millimeters, and pin B is 800 millimeters. Substitute the value and we can get the force pin B of 4.063 Newton. Substitute in the equation 3 and we can get the force in pin A, which is 0.937 Newton. And then we can find the moment at constant from pin B and P3. So from pin B, it's 500 millimeters from P2, and P3 is 350 millimeters. You can find the distance from pin B by subtracting the distance from P2 and pin A. And we get 281.5 Newton for the theoretical, and 3.8 is the net force that we got from the experimental. Hence we get 570 Newton force.
Okay, so for the discussion, for the first part of the experiment, which is when the variable is the distance between each load, after doing the experiment, we identify that the value of bending moment will increase when the load is placed further from each other, and vice versa. The bending moment will decrease when the load is placed close to each other. After doing the experiment and comparing the experimental value to the theoretical value, we can see that the average percentage error is 24%. This error could attribute to several factors, which is the accuracy of the spirit level when the bubble inside the spirit level is not exactly in the right area, and the surface of the beam might be interrupted by something which makes it not flat, thus affecting the value of the bending moment. So this error could also occur if the load hanger is not stable. It might be moving when we place the load and when we measure the spring scale value. And then for the part 2 of the experiment, which is the variable is the difference of load, we obtain that the value of the bending moment will increase when the load is increased. So the higher the weight we put on the load hanger, the higher the bending moment is. Between P1, P2 and P3, the value of the bending moment at P2 is the highest, which is the one that we fix at the middle, the closest to the hinge. It is the highest because it is the closest one to the hinge, while the value at the P3 is the lowest because it is the furthest from the hinge where the spring scale is. And then the average percentage error when comparing the value of theoretical and experimental is 47%. For this one, the error could attribute to several factors also. One is the placement of the load. The load might not be placed centrally at the load hanger. It might not be placed at where the load hanger bar is, so that might cause some error. And then the other one is the accuracy of the load value. Some of the load might not be weighed accurately to the value that it is stated on the weight.
As for the conclusion, the experimental and theoretical value are slightly different due to some error. Despite the differences between experimental and theoretical value, the result of part A and 2 has explained the relation of varied distance with bending moment and varied load with bending moment that is proportional. To improve the experiment result, make sure the reading spring balance scales can be taken and the eye must be perpendicular to the scale.
For the safety procedures, the first one is wear appropriate attire, gloves to prevent hand injuries, and covered shoes to prevent injuries if the weight hits your leg. And then check all the equipment for any sign of damage before starting the experiment. The third one is to make sure that the setup is stable and securely arranged. This is to ensure that the adjustable beam support are tightened and the beam is positioned straight and correctly to prevent slippage. And lastly, cautiously adding and removing the loads to make sure that we avoid it from falling and causing injuries, and do not overload the load hanger.